Hey there, everybody. We'll go ahead and let folks start settling into the Zoom room here. Welcome, welcome. I hope everyone is having a wonderful Wednesday afternoon, Wednesday evening, depending on where you are at. I know here in Oregon, we have beautiful blue skies, which is very rare for the Pacific Northwest fall, so very exciting. Go ahead and navigate to the chat box at the bottom of your Zoom window. It just looks like a little speech bubble. Let me know in the chat if this is your first Vernier webinar or if you're joining us for a second time, and what the weather is like there. I'd love to see how you are experiencing this autumn, the fall weather that we have going on. So make sure when you are leaving your chat in there, make sure it's set to everyone so that anyone who is looking at that chat box can see what you're typing. That also makes it easy for us to answer your questions so that we don't sound like we're talking to ourselves, so people can see what you've asked. So go ahead and drop in the chat how sunny and 65 in North Carolina. Awesome. Thanks for joining us today, Judy. Anyone else? Awesome. Nice to see you, Richard. Looks like it's your first time here. Sunny autumn day in Kentucky. That's awesome. Welcome back, Julia. Awesome. Very cool. Well, it looks like we have some first timers and some returning folks, and it looks like it is sunny across the board. So exciting for us for a sunny day. Now, I want to make the most of the time that we have, so let's hop into our presentation. I know I have some quick housekeeping items to cover before we dive right in. Let's see. Do you mind pulling up the presentation?
Yeah.
Awesome. Anyone new that's joining us, we were just all chatting in the chat box at the bottom of your Zoom window about whether you've joined a webinar before, a Vernier webinar before, and what the weather's like there. So if you want to drop it in there as we're doing this housekeeping, we'd love to hear from you. As I mentioned, I have some housekeeping items. First and foremost, a recording of this webinar will be live both on our website as well as our YouTube channel. It typically takes us about 3 to 5 business days to get that posted, and as soon as it's live, it'll be not only on those pages, but you'll also receive the recording straight to your inbox. So keep an eye out for that. You'll also receive a link to our public folder that I'm going to drop in the chat here in just a second. We'd love to answer your questions during today's session, so please put your questions in the chat box. If we don't get to it, or if I am just stumped, go ahead and email us at physics@vernier.com. So do ask us your questions. I can stop Josh and ask, or I'll just send you straight to the email and we'll get you an answer lickety-split. So those are my housekeeping items. Back off to you, Josh.
All right. Thanks, Dylan. So by way of introduction, I am Josh. I work here at Vernier. I'm a physics and engineering specialist. I want to know a little bit about you as well. So Dylan's going to post up just a short poll, just 2 questions. I want to know what grade level you teach, and then also how familiar you are with Vernier. That'll help me as I do this webinar to kind of make sure I can cover all my bases. So I was a high school physics and engineering teacher in Northern Virginia, just outside of DC. I taught all levels of physics from conceptual physics to AP physics. And in all those classes, I really loved hands-on doing stuff. And so I naturally gravitated towards Vernier, and I eventually ended up here. It's a great place to work, and I do all sorts of things. I do a lot of teacher trainings like this. I help with product development. I do a lot of customer service stuff. So if you were to call or email with a question, a physics question in particular, or engineering, I'm likely one of the ones that will answer those questions. And as Dylan mentioned, during this presentation, if you have questions, please feel free to post them in the chat. Dylan will interrupt me if necessary, and I do expect that at the end of the presentation, we'll have time to answer questions as well, you know. Dylan just posted a folder, a Google Drive folder to the chat. If you click on that link, it'll take you to the folder that has this presentation that you're looking at now. It also has the three kind of labs that I'm going to overview here during this presentation. So those labs there are two that are kind of two variations on this projectile motion lab that I'm going to talk about, and then the third one is a little bit different. It's projectile motion, but it's using Vernier video analysis. And the instructions are there. The teacher information documents are there as well. So if you want to do this activity in your class, you've got what you need there. All right, let's look at the poll here. So it looks like most of you that responded are high school. We tend to skew towards college, high school. That's good to know. And wow, nearly everyone here is an experienced Vernier user. That's great. I tell you what, it is great to talk to folks that have used our sensors in the past, because there's lots of little cool little details about these and how you use them, and making the most of them. And I'm glad I'll be sure to talk about some of those little details today. All right, so let's talk a little bit about like the standard projectile motion experiment. I'm going to switch my camera here. I don't know if it's how much of a difference it's going to make. Maybe I'll stop sharing for a moment so you can see it well. This is kind of like the standard projectile motion experiment is this. You know, you have a table, you've got a marble, you're going to roll it off the tabletop, and you're going to measure how far from the edge of the table it lands. And it's done a number of different ways. Most people will end up stacking up some physics textbooks and making a little ramp with a ruler. This is one of those rulers that has kind of like the groove in the middle, so it's perfect for a marble to roll down. I know some folks will actually like they'll take a piece of cardstock and they'll fold it into a ramp and cut it so that it's nice and smooth, that sort of thing. But the marble works just as well. And the way this is done, most people are going to they need to know the speed with which the ball is rolling across the tabletop before it leaves the edge. And there are a number of different ways of getting that speed. The way that we're going to kind of focus on today is using Photogates. But as the webinar is titled, you really can just use stopwatches and meter sticks and that sort of thing to measure. And we'll talk a little bit in a minute about kind of like the pros and cons of doing it that way versus a Photogate, or for that matter, a projectile launcher. So the marble rolls off the tabletop through your Photogate, or you've got your stopwatch there and you're recording how long it takes, off the edge, and then it enters free fall projectile motion, and you measure how far from the edge of the table it lands on the floor. That's kind of like the general idea. There are lots of different variations of ways that teachers do this. Some teachers are going to not allow students to actually measure how far. Instead, they're going to do this a little bit later in the learning cycle, rather than figuring out, well, what's the relationship between that speed and the distance that I measure on the floor. They're going to say, okay, we know this relationship, and they're going to say, I want you to figure out where it's going to land. We're going to predict it. They're going to sometimes they'll put a bullseye on the floor, and the students are responsible for placing that bullseye right in the same spot. A lot of teachers will use something like a cup or as a target. They say, you tell me where to put the cup, and then you're going to show me that you know how to do this and predict where it's going to be. I've seen some teachers get really into this, and they'll put their cup on like a constant velocity car and have it driving by, and the students will have to time it and place it just right so the marble still goes in the bucket. That's a little bit different. Other teachers, what they'll do is instead of just rolling it down a ramp, they'll actually launch it off the table. Somebody reached out to me just a couple days ago about how they use like a pull cue, and instead of using a marble, they have this like a nice sized puck, and they use that to knock it off the table, and they can very easily change how hard they hit it so that you get lots of different velocities, and they can measure it that way. We have this is kind of like the Vernier projectile launcher. It can be used to do the same sort of thing where you launch it at a certain at a speed, and then you can measure how far it goes. So there are lots of different variations there. It's all kind of the same sort of thing. It's still that same relationship between, you know, the horizontal velocity tells you a little bit how far, how long it's in the air is determined by how high it is. One of the things that you'll notice in the lab, as we have written, is that you use a plumb line in order to figure out where exactly the bottom of the table is that you're measuring from. That's kind of an important piece for everyone. I'm going to go back to this slideshow and talk a little bit more about some of the details of the Photogate versus the projectile launcher versus just meter sticks and table stopwatches and so on. All right. So when I first started doing this, I was a brand new teacher and I had this Vernier stuff in my classroom, but I didn't know how to use it yet. But I wanted to do this lab, and so I just use stopwatches and meter sticks. That's pretty easy. Kids understand stopwatches, they understand meter sticks. That distance relationship, the distance is equal to velocity times time. It's often where you start when it comes to kinematics, and it applies, you know, like students kind of understand that there. And so if you just put down a pair, we would take down a pair of stripes on the tabletop, and they would measure the amount of time it took the marbles to go from one, you know, line to the next line. And we'd measure that out. Usually it was something on the order of like 20 centimeters. And they would take that 20 centimeters and they divide by the time, and they would get a speed in centimeters per second. And that works. You know, it's simple, it's inexpensive. The downside to it is that it's a little hard to get really accurate velocity data from that, because you're really limited by human reaction time, you know, and teenagers, bless them, they don't always aren't paying attention. So sometimes it took a lot of time to gather enough data to be able to consistently say how fast that marble was going to be going. I like doing the target version where you'd lay down a target and they'd predict where it was going to land. So they really needed to know that velocity well. They needed to know not just that velocity, but kind of like how much wiggle room, right? How much did that velocity vary from run to run? And it just took a lot of time to collect all the data. That data collection time shortened dramatically when I started using Photogates. When I was teaching, this was before we had these Go Direct Photogates. And instead I would use two Photogates like this. You know, this is the standard Vernier Photogate that we've been making for, you know, 25 years. It's just a single beam, and I would use a pair of these, and it was just like the meter stick and stopwatch setup. I was measuring the time between the two Photogates, and then the software would tell what the distance was. The software would give us that speed, and this worked great. You know, they could just roll the marble down, and the Photogates would trigger, and the Photogates were always paying attention, and you get great data. We would usually do something like 10 runs. You know, you'd roll the marble down the ramp 10 times, each time leaving from the same spot, and you get a pretty good, accurate, precise measure for how fast the marble was rolling. This worked great. I really liked it. We had these Photogates already, but there was a little bit of a learning curve. Obviously, like both for myself and for the students, like how do you use the software? How do you set it up? For this particular experiment, I've got two Photogates. So how do I set it up so that the software knows that this first Photogate is going to start it and the second Photogate is going to stop the timing, that sort of thing. That is, like I said, there's a little bit of a learning curve there. I'm going to talk some more about that in a minute here when we get into some of the details about Photogates. But that really, I love that, and it worked really well. And it was kind of my entry point into really doing a lot of Vernier labs. If you really love projectile motion, some people really, this is you know, it's kind of the culmination of all the kinematics you've been doing. So like projectile motion is, you spend a lot of time there. Well, the projectile launcher offers a whole lot of options. The projectile launcher is really just like ours is pneumatic. You pump it up and it launches the projectile out the barrel here. And the barrel has two photogates built into it. Those two photogates are exactly 5 centimeters apart. Uh, on the back of the the back of the projectile launcher, it gives you some helpful details of like where the center line is, where exactly the center, where the launch point is, and that sort of thing. And for the beginning of your projectile motion unit, you could actually just set this up horizontally and have it shot out horizontally, and just do the same, essentially the same lab, but you're using the launcher instead of the just rolling the marble down. In fact, that's so common to use a projectile launcher for this lab that we have two labs written. One that uses just a ramp like this, the other one that uses the projectile launcher. You can find those two labs in the folder that that Dylan shared here. I'm gonna go back to that real quick, and so you can see that. So in that in the experiments folder that Dylan shared with you, there is a right. All right. There's these two activities. This one is the one we just discussed, the first version that most people do. The projectile motion one is very similar. It's, in our Physics with Vernier book, it's 8A versus 8B, and you can see it's the same idea. You're just launching the projectile off. Again, you use that plumb line in order to know where exactly to measure from. But they have you just like before, you're going to measure that distance. It's a little more exciting, obviously, and but it's really a great sort of thing. You kind of take 10 trials, you figure out your maximum, your minimum, and again, you're aiming for a target. You're predicting a range, and then seeing how well that prediction is works. The actual impact versus a theoretical one. So you'll see in this folder here, there's those two versions of the lab, 8A and 8B. There's also the teacher information for each of those. That'll give you some sample data. It gives you lots of great tips and tricks for getting good data, helping your students collect good data with both the Photogate and the projectile launcher. The last way to really do projectile motion is the last way to do projectile motion is to do it using video analysis. So in video analysis, you record a video, you import it into the software, and then you collect data by kind of laying data points on top of an object in that video. I'll show you some more about that in a minute. But it's really a cool way of doing it. Kids find video analysis really engaging because it's like something you'd see in the movies. You're analyzing this video. And there are lots of real world connections there. I'll show you a video that is very much staged. It's this same, experimental setup with a marble rolling off a tabletop sort of thing. But that's just the beginning. You can take all sorts of cool phenomenon, record them with a video, with a camera, likely a camera that you just have in your pocket, and then analyze the motion of something moving in there. There are some downsides. I find that, well, there's, besides the cost, you have to purchase a license for the software. I don't know if it's just because as a parent, I have become very mindful of the amount of time that my kids spend on a screen, but it is an activity that is mostly on a screen. When you're rolling a marble off a tabletop or launching it, kids are very much engaged with the real world itself. And you feel like you're doing this, you're doing science, and it's great. When you're doing video analysis, you're very much on the screen, and it feels like it's just more time on the screen. So I count that as one of the downsides, because I want the world, we're trying to explain the world around us, the world we touch and feel. All right, so there are pros and cons to each of these different ways. I want to talk a little bit more about Photogates and then also video analysis, and kind of give you some, especially if you're going to do these projectile motion activity, just some guidelines, some tips and tricks about how to use those two tools to investigate projectile motion. So Photogates are probably the simplest sensor in the world. You know, all it is a pair of LEDs. One of those LEDs is a infrared emitter. It's shining infrared light, and the other one is kind of is looking for that light. It changes the voltage across it changes as that light falls on it. And so really it's a few resistors, a couple of LEDs, and what's coming out the cable is either a high or a low voltage. And the software reports that as simply as blocked or unblocked. So it's really simple, but as simple as it is, there can be lots of, it can get a little bit complicated. Most people use Photogates to measure a speed, you know, and if it's a lab, what we would call like a LabQuest Photogate, like, you know, like I use in my classrooms, chances are you're using a mode called gate timing, where you're recording how long the beam is blocked, and because you know how long the object is, you know how far that object traveled while the beam was blocked, and then the software gives you the time that was blocked, and you can use that to figure out a speed. You can measure all sorts of things with a Photogate. You can measure position and velocity and acceleration, so long as you have either multiple flags or multiple gates. Multiple Photogates kind of makes sense, right? If you have two Photogates and each one is measuring a speed, and you know how far those two Photogates are from each other, you can figure out an acceleration, right? When we say multiple flags, what we mean are the object is like, it's almost like it's passing through the Photogate multiple times. The way that you'll see that usually is things like a picket fence. So a picket fence, this is a piece of acrylic that has you know, these bars on it, and we know that they come at a regular interval. It's 5 centimeters from the one edge to the edge of the band to the next band as well. So that's 5 centimeters. And if you drop that through a Photogate, you're going to get a speed for each of those bands, which allows you to then figure out an acceleration. You know the speed for each of those. And that same idea is used other places as well. This is a dynamics cart, and it has a picket fence mounted on it that allows you to measure its speed and acceleration as well. It's also bands. In this picket fence, you can flip it upside down if you want just a single flag on the other side as well. And then the other place where you might see this with multiple flags is this is a pulley that has been mounted to a bracket, so I could mount it on the end of a dynamics track. And that pulley, I know this is a 10-spoke pulley, and I know how far the wheel has to turn, the pulley has to turn in order for one spoke to move through the Photogate. And so I can get distance and velocity and acceleration from that pulley as well. So Photogates, as simple as they are, they're really versatile, and you can measure all sorts of things with them. But there are some tips, some things to consider as you work with them. As I mentioned before, gate timing. This is where you have an object just pass through the Photogate, and you measure, you know, how far, you measure the size of the object, so then you know how far it's traveled as it passed through the gate. That really, it's really critical that the Photogate beam is kind of, you know, passing through the middle of the object, or rather the distance of the object as it passes through the Photogate, that you enter that distance correctly in the software. The accuracy of the velocity that you measure really depends on that distance. And so if you're rolling a marble through there, the easiest thing to measure, the easiest distance to measure on the marble is its diameter, which means you want the beam of the Photogate to pass through the diameter of the marble. And so that might mean you might need a little tripod, you might need like a ring stand or something like that, so that you can precisely line up that Photogate so that it passes through the middle of the marble. The photogate beam is passing right through the middle of the marble. That can be really tricky sometimes, especially if you have to worry about, like in this particular lab, you've got a marble rolling across the tabletop. Often what happens is if marble transitions from, like, say, the ruler or the ramp to the tabletop, it bounces a little bit. And if it's still bouncing as it moves through the photogate, you might end up with a lot more, a lot greater variability in the velocity that it's recording than you would expect. And so one way to get around that, to not have to worry so much about the alignment between the beam and the object, is you use two photogates. If you use two photogates, then it doesn't matter like how the beam intersects the object, because you know the distance between those two photogates. You can say, okay, I've got these two photogates here. They're 20 centimeters apart. So the time, the distance that needs to be recorded is always 20 centimeters. I know that distance all the time. In fact, that is such a common way, such a common data collection mode. We call it pulse timing. That the new photogates, these are our Go Direct Photogates. They're the new fancy USB wireless Bluetooth ones. They are they have two photogate beams built into them. This one, the two photogate beams are 2 centimeters apart. If I pass my hand through here, you can see that there are the two LEDs light as my hand passes through. Those are the two photogate beams. And that way, when I use this photogate, it's like I'm always using pulse timing. So any velocity I measure here, it tells me I don't have to worry about whether the object is bouncing or not. I don't have to worry about how long the object is. As long as it's passing through there and it's breaking both beams, I get an accurate speed. The added advantage to that is because it knows which beam is being broken first, it can also give me a direction, a positive or a negative direction. So that works out well. The last little bit about photogates that I always share with folks is that our software typically gives you a graph, but when it comes to looking at photogate data, often the data table is more helpful than the graph, especially if you're just recording speeds. You're doing it 10 times or something like that. The graph the graph isn't as helpful. It's going to be about the same sort of thing. And if you look at something like a picket fence, you will get a position versus time graph, but sometimes interpreting that is a little bit difficult. If you look at the graph, especially if you teach yourself and your students how to interpret the data table, it makes it easier to understand what's happening and why you're getting the data that you are. Linda asked a question in the chat that is a good one. She said, how does a photogate, why would you use a photogate over, say, a motion detector? And I've done another webinar not too long ago about motion detectors, and they're really versatile because you can toss a ball above it and you get this nice position versus time graph. You can move your body in front of the motion detector, and again, you get this great position time graph. And typically, when you're talking kinematics, you're teaching kinematics, it's those position, velocity, time graphs that you want to get to. And with a photogate, typically you think of this is like it's taking just a snapshot of the motion at one particular moment, and it's not like you don't get that full picture like you do with a motion detector. You do get something close to that with, like, say, a picket fence. You might get a little bit of a little section of motion, of position, velocity, and acceleration, but it's still really just a snapshot. You drop this picket fence, and you're really only getting the motion of the picket fence right around here where I've got my photogate, not below that or above that. Photogates have the advantage that they tend to be able to capture the motion of smaller things than a motion detector can. A motion detector would capture the motion of this cup, as you're using this target, just really well. It's big enough, it's got this nice flat bottom to it that it would measure. But if you had, for instance, like a marble, and you tried tracking the motion of that marble with the motion detector, it'd be really hard. It might capture parts of the motion, but you'd probably end up with a lot of noise or nothing at all. Whereas the photogate, all it's got to do is break that beam, and that beam is pretty darn small. And so you can capture motion for some objects that you can't with the motion detector. Another thing about the motion detector or the Photogate is the motion detector has a somewhat limited range. It's typically, most people can get like a good 2.5 meter range out of a motion detector, which in most classrooms is great. But if you're going to do, like, say, a mousetrap car experiment, and you want to know, like how far how long does it take to go 5 meters or something like that? The motion detector it's not going to be able to record the whole motion, but you can use some Photogates to capture that whole motion. In the past, with our older LabQuest, these wired gates, we've sold these Photogate extenders, these cables that make it so it's really long. The cable's really long, and you can use something like that with the wireless ones. If you use two, you can record it that way. If you have if you really care about how precise that measurement is, that time measurement over these, say, 5 meters or something like that, these do have an auxiliary port that will allow you to like physically hardwire them together so that you can also get the same precision accuracy you do when they're wired, as if they were wired together. The last thing about motion detectors versus Photogates, and this is kind of a fun thing, is Photogates, for the most part, the object has to pass through the gate in order to measure its motion. But if you use a laser pointer, you can actually make your gate as big as you want it to be. There was one of the newsletter articles that inspired me when I was in the classroom that I read in the Vernier caliper was a physics teacher had taken his class into the gym, and they were talking about pendulums and had kids swinging on the rope, and they measured the period of oscillation of these pendulum kids using a laser pointer. The laser pointer was forming the beam, and it would block when the students swung through, it would block the beam, and then every third swing through there, you had gone through one oscillation. That was pretty cool as well. That's also something that would be really hard to do with a motion detector. I mentioned that the projectile launcher has two Photogates built into it. Those Photogates are set up to do, the reason why there are two there is for the same reason that I mentioned before, that you have a known distance between them, and so it doesn't matter the size or how well it breaks the beam or line. So long as it breaks the beam, you're going to get a good accurate measurement. All right. So Photogates. I'm going to do, what time are we at? Oh, maybe I'll skip. Photogates, in this particular lab, you might use your Photogate to collect 10 speed measurements and then average them out. Look at what was my maximum speed, what was my minimum speed, what was the average. And that gives you, especially if you can predict where it lands, that gives you an idea of, well, like, how far might it land? How close might it land? Where is it most likely to land? And that gives you a good idea so that you can accurately predict where it's going to land. All right, let's switch gears here real quick. Let's talk a little bit about video analysis. So, I'm going to first take and I think I'm going to copy this license key into the chat here. So, video analysis, you take your phone, you take your camera, you record the motion of an object, a moving object, and then you use this software to kind of collect data, drop data points on top of that object, and then use that data to then do the science. How fast is it moving? How far did it move? That sort of thing. We've done video analysis for a long time. Our Logger Pro software, it's been around for 20-something years. It has video analysis features built into it. These days, we have a standalone Vernier video analysis app that it just runs within a browser. It takes all those tools and puts it in a nice, neat bundle. And if you want to try for Vernier video analysis, click on that link that I put in the chat, and it'll open the app within your browser window. It works best in, I think, Chrome and Edge and Safari. And you can kind of follow. I'm going to do a quick demo here of video analysis, so we can kind of see also, like, what is this good for? What is this maybe not so as good for? Why might you choose to do this over, say, a hands-on lab with Photogates or meter sticks and stopwatches to talk about projectile motion. So I'm going to go, I've got video analysis open here in a separate window, just in a separate tab. You can upload your own video, and you'll see that the activity that I've shared in that folder, the first part has students analyze this sample video here, this basketball shop sample video. But it also has the second part of them has actually students that they make their own videos and upload those or into the app and analyze their own videos. You would import it just by clicking on this button here. You'll see there are a few sample videos here. In fact, this one that's called ball and table is just this same activity, where you've got a ball that rolls across the tabletop and then off the table, and you measure. You track its position along the tabletop, and then as it falls to the floor, and you figure out its speed. You figure out how does that compare to how far it landed, that sort of thing. The way that this works is you have to track the object. So I'm going to go here. This video was created by RIT, Rochester Institute of Technology, years ago, 2008, but it's worked beautifully, and so it lives on here in Vernier Video Analysis. And all you do is collect. You can just kind of click on top of the object as it moves along. Every time you click, it's going to advance the video one frame, and so you can drop another data point. When you're collecting data on something like a ball, you can either eyeball the middle of the ball, or I find sometimes it's easiest to pick apart a point on the ball and follow that same thing. So for instance, I'm going to click on, I'm going to actually make this a little bit bigger for myself. And I'm going to click on the very top of the ball. Sometimes it's a little easier to track than I feel like eyeballing necessarily the center of the ball each time. And as I click, I get some data here. You can see that over here, I'm getting, it's filling a data table, and it's graphing that data. If you look carefully, you might notice that the units are a little bit weird. All right, it says it gives me an X and a Y, so a horizontal and a vertical position, and a velocity for each of those. But the units it's giving me are px. That stands for pixels, and all it's doing is saying the lower left corner of the video frame is 0, 0, and it's just telling me the pixel locations of those data points that I'm dropping there. If I want to convert those pixels into an actual distance, like meters or something like that, I need to give it some more information. And that information you provide by telling it more about the system. So I'm going to click, I'm going to move this back over here, and I'm going to go to my system. And one of the things that it asks for is move to a known separation. So I'm going to go back to the very beginning here, that first slide, and I'm going to move these two circles so that they overlay exactly 1 meter. Right, so I'm going to move this here, over here, and by doing so, my data table updates itself. So now, instead of giving positions in pixels, it's giving me positions in meters. And you can see what the conversion factor is up here. By moving these two circles to this distance here, right, it's saying that 317 pixels is 1 meter. And I can choose an origin as well. And typically an activity like this, you'll probably put it right at the end of the track, right on the floor sort of thing, and say that's what I'm going to call 0, 0. And so now I can see that my X positions as it rolls along the top here are all negative values. And then you can do, with the same data, once you've collected all your data, you can then, do curve fits and all that stuff that you would do to analyze the video. What does the horizontal motion look like? What does the vertical motion look like? I'm gonna switch gears here, and I'm gonna go back to that basketball shot video just to show you one additional piece of this, and that is that the app does object tracking as well. So if you set up your videos right, in this case, by right, that means if you set up your video so the object is moving behind in front of some boring plain background, you can get it so that it will track the object by itself. So I'm going to wait. I'm going to advance the video till it's just to the left his hand, and then I'm going to use the auto tracking feature here in Vernier video analysis. I'm going to kind of zoom in on my basketball. This is Joel Matikowski. He's a physics teacher here in the area. And I'm going to start auto tracking, and it's going to collect data for me. And I'm going to see these nice that nice parabolic curve that I expect to get when it comes to projectile motion. The object tracking worked great until it bounced. The app has a little bit of physics knowledge built into it. So if it notices that there's a really large acceleration, it stops and says, wait a minute, something going on here. So I can see here's my the vertical position of the ball is that nice parabola I expect. I can see that the horizontal position of the ball follows this nice constant motion, constant velocity pattern here. And the same sort of thing we've got. You can create it, you set your system. There's a meter stick here on the ground. You can choose an origin, and you can do your same projectile motion lab just with video rather than with meter sticks and stopwatches or Photogates and that sort of. So that's kind of an overview of Vernier video analysis. It kind of projectile motion is like the thing that most people use video analysis for, but with the data collection tools that are in the app, you can also use, you can calculate energy and momentum and that sort of thing. So you can actually do all sorts of activities with video analysis, not just projectile motion. All right, let me see, what have I forgotten here? That link, if you tried Vernier video analysis in your own browser window, that link is good for, I think, until October 30th. So you can try that again later if you'd like it. Like I mentioned, in the lab, there is, or in the folder in the Google Drive folder, there is a lab here. This first one, it's number 4, projectile motion. That uses Vernier video analysis. And if you want to try that lab yourself, you can use that 2-week license for Vernier video analysis to try it out. All right. I think at this point, we're at questions. What questions do you have? Feel free to post them in the chat. Dylan posted a survey in the chat as well to let us know how you felt about this webinar, if there are other webinars that you'd like to see from us. What questions do you have about Photogates or the projectile launcher or Vernier video analysis? Let us know. The time of flight pad. So let me show you what this is. This is the time of flight pad. It looks, oh, sorry, over here. It looks, all it is like it usually doesn't have the yellow on it. We put this in the yellow on this so that it doesn't walk away from the physics lab. I'm sure you never have to worry about sensors walking out of your classroom. But this is, all it is kind of like a semi-squishy little pad. And when something falls on it, it registers kind of like a Photogate. In fact, if you were to just plug this straight into like a LabQuest interface and then connect it to Graphical or to Logger Pro or LabQuest or something like that, it just shows up as a Photogate. When it's being pressed, you get it's like it's blocked, and when it's not pressed, it's unblocked. Typically, you would either use this with the projectile launcher. If you do, it just plugs into the projectile launcher itself, and it works as it's kind of like you can get it as to measure the time of flight. You put it where you expect the projectile to land. The way that you set it up, if you're in, it's a little bit different from Logger Pro to graphical analysis to LabQuest, but chances are you're using graphical analysis or LabQuest, and in both of those, you'd go to the data collection settings, and there's an option when it recognizes, oh, you have the projectile launcher connected. There's an option where a box that you check that says, I also have the time of flight pad. And when it does that, when you check that box, it will actually add another column to your data table for that time of flight data. If you use this as a Photogate with a regular Photogate, so like say you want to have this set up horizontally, and you want to drop a marble here, and you want to know how much time does it take to go from this Photogate to this time of flight pad, you would plug both of these into a LabQuest interface connected to Logger Pro or Graphical Analysis. They would both show up as Photogates, and you would use what's called pulse timing. That's the timing mode that it wants. In Graphical Analysis, you would say that you want to set it as a timer, and it would give you that pulse time. In LabQuest, you also the mode is called pulse timing, which would be the time between the two gates. And in Logger Pro, it's the same sort of thing. You'd go in there to data collection setting and say Photogates pulse timing. So it's kind of handy. It's a great, if you get the projectile launcher, this is a great accessory to get to grab with it. You probably only need like one of these, just so if you want to demonstrate time of flight and that sort of thing, you could do that with a projectile launcher. So Stephanie asked a little bit about the projectile launcher and how reliable it is. There are lots of different ways that you could make a projectile launcher. We went with a pneumatic system, where this is actually like a bicycle pump that you pump up. We did that because it is very reliable. There's a range knob on the projectile launcher, and if you don't use the range knob, you don't adjust the range knob at all. So that is to say, if you're not fiddling with this range knob in between runs, you get very precise speeds from one launch to the next. So you'll, in fact, as you start pumping it up, you'll hear a point at which it starts to blow off. It's like it's not pressurizing anymore. It's just letting that extra pressure blow off. And that is set very precisely by this knob. So most of the time what you'll do is you'll launch it a couple times and fiddle with the knob until it's launching at a distance that you want it to, about, I want to go about that far. And then once you've got it at that point, then you can fire it. As long as you don't touch the knob, it'll be really repeatable. It'll be really, from one shot to the next, it'll always be the same speed. Yeah, so April asked a little bit about what equipment might be most useful for a conceptual physics class. There is a lot. I have a lot to say about that, April, but I think that might be easiest to do over email. So I'll have Dylan, we'll look up your email address, and I'll send you an email after this webinar to reach out, and we can get that conversation started. Especially in like a conceptual class, you might lean to some equipment versus others, just because sometimes it's less important for you to get like super precise data. And if you're really just kind of talking about general concepts, you want to look at the shape of the position time graph. You don't necessarily need to know exactly what those precise numbers need to be. All right, let me see if I missed any questions. All right. Well, I appreciate you hanging out with me today. As Dylan mentioned before, please, if you have questions, reach out. You can email. We have a little chat bubble on our website. You can call. Dylan's going to send out a follow-up email in a week or so with a recording of this webinar. You can always reply to that. We're happy to help you, especially those of you that are experienced Vernier teachers. You've got all this equipment. If you've got ideas about how you'd like to do an activity or an investigation, and you got these probes and you kind of want to know how it work together, we love answering those kinds of questions. If you got equipment that's not working for you, it's like, I don't know why this isn't working like I expected to, give us a call. We can help you figure it out. And we'd love to. Dylan posted that survey. Give us feedback about this webinar. Let us know what you'd like to hear from us. and we'll do it. Thanks.
Thanks, everyone. Have a good one.